Today we're going to try to fling the magnets off a MAVILAR motor. Just kidding, we're not going to go that fast. Only 10,000 RPM. The magnets probably don't fling off until about 20,000 RPM. There's a special design on the Extra Force Prime AC servo motors from Infranor. Mavilor makes the motors. I think they're Spanish because Extra Force is spelled funny, F-O-R-S. Anyways, let's take a look at the data sheet for the Extra Force Prime motor. Yeah, high speed, no cogging. That's an interesting feature. So when you turn the shaft of the motor by hand, you can feel it's really smooth. So they did something in the design to make the cogging really low on this motor. Reasonable torque ranges and speed ranges, plus some high speed capability due to the construction and design of the motor. Yep, it's a slotless stator design. That's how come it's so smooth. High speed, zero cogging, minimal torque ripple, high efficiency, high rigidity. Very demanding applications is what they say. Now all the rated speeds here, or the normal speeds as they call it, look like 3,000 RPM. But you can see in the speed torque curve that some of the motors have a much higher speed range, and upwards of 10,000 RPM. There's a little drop off, maybe some IR drop. It goes out pretty flat, and they just cut the graph off. Maybe further out at 20k RPM is where the magnets fling off. Anyways, we're going to take a look at this motor with CME2. So I've got my Xenus compact here, 120 volts AC, 7 amps continuous, 15 peak, driving this similar to size 23 motor. Serial cable connection, 24 volt, motor power, motor feedback, incremental encoder with Halls, STO bypass jumper, AC power, and there's my Meanwell 24 volt supply. So just take a quick peek at the basic setup. It's a brushless rotary motor, incremental encoder with Halls. They have other feedback formats, various they say. Sine cosine is pretty cool. NDAT is absolute with sine cosine usually, so you get absolute position. We normally don't talk about hyperphase, but incremental encoders, resolver is another option they have too. Anyways, this is just going to be in a incremental encoder with Hall position mode. Sinusoidal commutation. We can buffer the encoder output, that's fine. The motor, here's some motor information, and this was in the data sheet that I had at this value, 11,400. So we'll just say, I'm not going to recalculate the values, but when you calculate the values, the V limit gets set to 5,000 RPM. So I'm going to use the CME2 scope to make a move. I put a little tab on the motor so we can watch it spin. This is 8192 counts per rev, 10 revs, 100 revs. Going to go at 4,000 RPM. So no problem. 4,000 RPM. Everything looks good. I'm gonna ask it to go 5,000 RPM. It'll do it, but there's a velocity limit set at 5,000. So we can't go any more than that. We're going to get a following error. Actually, this number should be 10% greater than any command I give. Yeah, the trajectory generator is much smaller than that. So if I try to set this to 10,000 RPM, actually I need to set it higher than 10,000. So we'll go 20% higher. And that exceeds the maximum velocity limit set on the motor screen. So I have to go fix that. So on the motor screen, I'm going to set it to 12,000. I'm going to say okay, save it to flash, no, Do not calculate all over again. It'll just write 6,000 over the V limit that I just set. So, okay, I'm going to enter 20% greater. It's telling me I'm going to run out of bus voltage. So I may have to crank up my bus voltage here. I got a variac, we can do that. But let's see if we can reach 8,000 RPM without any problems. Alright, it's good tape. Sticks on there pretty good. So far so good. I'm going to trace a few things like voltage limit warning. I want to know when I hit a voltage limit. Voltage bus, we can look at the power supply while we're going fast. That should make things interesting. So 100 RPM or 100 revs in less than a second. That's pretty good. You can see the bus pumping up. You can see the ripple voltage and the droop on the DC bus. So I'm down from 200 volts a little bit. I got a variac here cranked up, so I get a little bit more than 120. But I'm going to try for a speed of 10,000. Alright, that's 80% of the velocity limit. That's okay. Well, so far so good. Let's go faster. At some point, we should be able to fling the magnets off of this thing. No problem there. Well, I'm exceeding the ratings, but that's okay. It's my motor. I can burn it up if I want. So we're going to increase the limit some more. See how fast we can get this thing before it starts having some problems. So let's set the velocity limit to 15,000. Yeah, maybe that's just below the speed at which the magnets fling off. So I'm hoping to hit a voltage limit pretty soon. Well, that's pretty fast too. I saw a warning there. So reading trace data. Here we go. We are continuously voltage limited at this speed. So the following error grows exponentially as we make the profile move. So pink is profile velocity, following error is in blue, bus voltage is in green. I'm going to take a look at voltage terminal servo, which is the Q vector of the field-oriented control. And I'm going to ask it to go just a little bit slower. Just want to tickle that voltage limit. I don't want to be constantly on a voltage limit. Okay, that was good. Let's add another 500 RPM and see if we can just bump into it. We should hit it right about here where the currents peak and the voltage droop is the most. Yeah, so there we go. Right at the end of acceleration, at the most voltage and at the most current, we get a few blips of voltage limiting. We can see here there's a difference between the voltage terminal servo and the bus voltage. This is not voltage available. There's also a Q voltage. There's a real and an imaginary part that add up to give you one voltage vector, which must lead the current vector because E leads I in an inductive circuit. But what we may be able to do to squeak out a little bit more is we can turn off the circular limiting on the I loop screen. So we'll go for max speed and see if we get a little bit of voltage back. Maybe a little bit. It's hard to tell. Fewer blips. I'm going to see if we can go to 12,000 because that's my new goal. Even faster than 10,000. That seems to be okay. You know, you have to watch out though. You know, if you're at 12 amps and you've got a 5 ohm resistance, you know, that's like 50 volts. So right now I'm running on 200 volts rectified. That's a little bit more than 120 volts AC. So to do this reliably, you would probably want a 208 volts AC, or 230 or 240 volts AC. If the regen gets bigger, put a little load on there. There's a dissipator in the Xenus compact, so that'll turn on and dump a little bit of energy. I like to say all the energy we put in, we can take back out. So continuous duty cycle of this type of operation should not be a problem. The last little thing I should look at is the actual current. When you increase the load, you get a little bit more current. So we're hitting about 4 amps for peak acceleration, and then for running about 2 amps. So we could do 3 amps all day, and we could do 3 times the inertia and hit 12 amps. What you will notice in the error log is while you're getting voltage limit warnings, so you'll see right now there's no warning, but we hit voltage limit 7 times and current limit once. Sometimes with a voltage limit, you'll get a current limit right at the same time, because there's not enough voltage to deliver the current we're commanding. So that's a common occurrence. So we can see the we're bumping into current limits every time we cycle the motor. So that's it for trying to fling the magnets off the Mavilar. Can't seem to do it. Need more voltage. Got to go faster. I didn't even fling the paper off the motor shaft. Okay, thanks for watching. Maybe next time we could do that.